Hi, this is John Whitaker for the Probability Graduate Level class, and this is our ninth video lecture. And Travis, Wayne, today we want to talk about the normally distributed random variable, and that's all we'll be talking about today. So let us begin by writing down what the definition of a normally random variable is. So here's the definition. It says a random variable X is said to be normally distributed I'm going to say with parameters mu and sigma squared if the PDF of x is f of x is equal to 1 over the square root 2 pi, in the bottom we have a sigma, times e to the minus x minus mu to b squared all over 2 sigma squared, where sigma is greater than 0. Okay. So, that's the definition, and of course one of the things we want to look at is if we can show that the integral over the whole real line is equal to 1. To that end, let us examine the following. So consider the integral from minus infinity to infinity of just this part, e to the minus x squared over 2 dx. So we're going to consider this. And the way that we're going to try to compute this integral, this is an integral whose integrand that doesn't have an antiderivative in the closed form. So to compute this, what we'll do is we'll look at that integral squared, and the way that we'll do that is say, what if we had an integral from minus infinity to infinity of e to the minus x squared over 2 dx? And then squared means times itself. So here, I'll rewrite this as minus infinity to infinity of e, and let's just do a different variable, e to the minus y squared over 2 dy. Now, if you think of this multiplication and look at them as an iterated integral, you can rewrite this as the integral from minus infinity to infinity, minus infinity to infinity of e to the minus x squared over 2 times e to the minus y squared over 2. Now I'll write down dx dy, which I'll rewrite as this double integral of e to the minus quantity x squared plus y squared over 2 dx dy. Now, what we'll do is we'll change to polar coordinates, and this can be rewritten as the integral, the double integral. And so here, this is e to the minus r squared over 2, where r is nothing more than the square root of x squared plus y squared. So this is minus r squared over 2. And then the dx dy becomes r dr d theta. And so here, our theta, to get the whole xy plane, our theta values can run from 0 to 2 pi, and r runs from 0 to infinity. And we can rewrite this, if you will. Okay, so here, if I integrate with respect to r first, 0 to 2 pi, this is e to the something, the derivative of something is minus r. I don't have that, so I put a minus there. And then I could integrate, because if I had this minus r, I would get e to the minus r squared over 2, evaluated from 0. I'll be very sloppy and write down infinity here instead of using the limit as t goes to infinity. And here d theta. So I'm being a little bit informal the way I'm writing this up. Okay. So for that evaluation is, as r gets really, really huge, r squared gets really, really huge. But that's a minus really huge number over 2. You get a huge negative numbers goes to 0. And so minus and minus becomes a plus. So we end up getting 0 to 2 pi is the interval we have. Of 0, and it can be plus. And here when I stick in 0 for r, I would just get 1. And here we have d theta. So this ends up being the interval of theta evaluated from 0 to 2 pi, which is equal to 2 pi. So what we found is that this interval from minus infinity to infinity of e to the minus x squared over 2 dx to b squared, because that's what we were looking at, that's equal to 2 pi. So, here's what we have. We have 1 over the square root of 2 pi times the interval from minus infinity to infinity. E to the minus x squared over 2 dx. That's equal to 1. Okay? So, that is a good result, because that's what we get when mu is equal to 0 and sigma is equal to 1. And so here, if we let u be equal to x minus, well, I guess I could rewrite this. Thus, we write 1 over the square root of 2 pi, integral from minus infinity to infinity, just changing the variable, of e to the minus u squared of 2 du, if that's equal to 1. Just changing the variables. And now I'm going to let u be equal to something in terms of x. It gets back to the variable x. So from where we are, if we just let, so if we let u, from that last line, be equal to x minus mu over sigma, then we have 1 over square root of 2 pi, integral from minus infinity to infinity. So this is in terms of x, because if u went from minus infinity to infinity, this x would as well. This will be e to the minus quantity x minus mu over sigma to b squared, all over 2. And then, I should have written here, let's don't forget that du would be equal to 1 over sigma dx. So we had a du, so I write down 1 over sigma dx. for this. And that's equal to 1 over square root of 2 pi. And then the sigma can be taken out because it's a constant. This would be the interval from minus infinity to infinity of e to the minus, well, it'd be quantity x minus mu, all that to be squared, over sigma squared, but we could put that in the bottom. Okay? Then that's what this part would be from the previous integral, but that previous integral was equal to 1. And that concludes what we wanted to. Okay. Here is a fact. And it says, this is not just for, this is for continuous random variable, not just normal random variable. But it says, if x is a continuous random variable, with a PDF f of x, okay? And let's say CDF, I'll write it down, VF of A, then the derivative with respect to A, the variable A, of F of A, big F of A, the CDF, what that's equal to is the PDF evaluated today. Let's prove this. Okay, so the proof, here's what we got. We got f of A is equal to the probability that x is less than or equal to A, which is equal to the interval from minus infinity to A of f of t dt. So, the derivative with respect to A of f of A will be equal to the derivative with respect to A of the interval from minus infinity to A of f of t dt. By using the fundamental theorem of calculus and working with improper integral and moving that derivative inside the limit, what we can get is that this is equal to a fundamental theorem of calculus, f of A. So that's what we have, that's what we want to prove, we're done. As this is by the fundamental theorem of calculus. The next thing I want to talk about is a fact. Says the following. It says if x is normally distributed with parameters mu and sigma squared, then the random variable that is defined by y equal to some number a times x plus some constant d is that random variable y is normally distributed with parameters a times mu plus b and a squared times sigma squared. So the proof of this is done in cases. And so case 1 is where if a is greater than 0. So if a is greater than 0, here's what we have. We consider f, if you will, of y, the CDF of x. Okay? What that's equal to the probability that y is less than or equal to x. Well, that's the same thing as the probability that ax plus b is less than or equal to little x. If you solve for x here, you subtract b for both sides of the inequality, and then divide by a. Since a is positive, we wouldn't have to change this direction of the inequality. So this is the probability that x is less than or equal to x minus b over a. And that's something we have a formula for in terms of we have the PDF of x. So this would be equal to 1 over the square root of 2 pi times sigma times the interval from minus infinity to this little x minus b over a. Okay? Then I'm going to write down the rest of the PDF here, but I'm going to call it as a function of t. So it's e to the, it would be minus t minus mu to b squared all over 2 sigma squared dt. Okay. Now, that's what we have. And so if we take the derivative, so the derivative with respect to x of f of the CDF of y of x, that's going to be equal to, well, here we would have, and I'll rewrite this. This is really nothing more than f of the PDF of x evaluated at x minus b over a. That's what that would be. Times the derivative by the fundamental theorem of calculus of x minus b over a, which is 1 over a. That's what we have. And so, here, by the previous fact, this is nothing more than the PDF of y of x is equal to, here, this would be 1 over the square root of 2 pi. Here I would have an a and a sigma. This is e to the minus x minus b over a minus mu to be squared all over 2 sigma squared, because that's what the PDF of x would be evaluated at x minus b over a, and then the 1 over a goes here. And that's equal to 1 over the square root of 2 pi A sigma E. This would be minus x minus b. It would be minus a mu to b squared all over this a that's in the bottom. I've got the common denominator with this mu here to get the a mu. All of this is over a to b squared. I'm going to put the a squared down here. It's 2 sigma squared a squared, which is equal to, one more line, 1 over the square root of 2 pi a sigma e to the minus, and I'm writing this down, x minus the quantity a times mu plus b to b squared all over 2 sigma squared a squared. So in this case, you can see, in this case, y is normally distributed with parameters. So I'm running out around here. With parameters. Okay, so the mu is a minus, or a times mu plus b. That's that part. And the other parameter is found right here, which is a squared sigma squared. Okay, so those are the 2 parameters. So that's what we wanted in this case. Well, let's look at the other case. The other case is where a is less than 0. In this case, it's very similar. So then f, so y, the CDF, evaluated x, y, is the probability that y is less than or equal to x. But that's equal to the probability that it was ax plus b is less than or equal to little x. And here, that's the same thing as the probability when you solve for x. You subtract b and you divide by it. But when you divide by a, you have to switch the sign of inequality. So it's x is greater than or equal to x minus b over a. But that's the same thing as 1 minus the probability that x is less than or equal to x minus b over a. And you say, well, wait a minute, they aren't mutually exclusive, but then this isn't exactly the opposite because of this equal. But for a continuous random variable, the probability that x is equal to something is 0. So the equality being here really doesn't change. It could be less than or equal, less than, and then you could put less than or equal to because they're the same. So if I take the derivative with respect to x, f sub y of x, that's the same thing as the derivative with respect to x of 1 minus the probability that x is less than or equal to x minus b over x. And so this is the PDF evaluated x. Is the same thing as this will be minus the derivative with respect to x. Well, the derivative of 1 is nothing. Okay. So this will be minus the derivative with respect to x, if you will, the integral, well, be 1 over the square root of 2 pi sigma integral from minus infinity to x minus b over a, e to the minus t minus mu to b squared over 2 sigma dt. Just like what we had before. And so what we end up getting here is equal to minus, this is 1 over the square root of 2 pi sigma in the bottom. Here I would get e to the minus, it would be x minus b over a minus mu all over 2 sigma squared, this is to b squared here, and then we'd have to take the derivative of this, which was 1 over a, and that's equal to, if you rewrite with the a having the minus associated to it, it's 1 over the square root of 2 pi minus a times sigma, e to the minus, this would be, again, x minus b minus a times mu to b squared, and in the bottom, we have 2 sigma squared, and then I have that a squared. And in this case, that is well, I'll write it down one more time. A little simplification. So that's equal to 1 over the square root of 2 pi minus a times sigma. Here this would be e to the minus, it's x minus, it would be the quantity a times mu plus b, all that to be squared, over 2 sigma squared a squared. Now look. That fits the exact right form, when a is negative, of what we want to be a standard normal. Because when a is negative, minus a is positive, and minus a times sigma is really the square root of sigma squared a squared. And that's what we want to be in that place. So in this case, y is normally distributed with parameters a times mu plus b and a squared times sigma squared. So in all cases, we got what we wanted. So that concludes the proof. Okay. Next thing I want to do is define a particular type of normal random variable called the standard normal. A normally distributed random variable I'm going to give it a symbolization of z is called the standard normal random variable. If the PDF of z is f of x equal to 1 over the square root of 2 pi e to the minus x, or I'll say z, squared over 2 sigma squared. That is z is normally distributed with parameters what's the mu? The mu in this case is 0, so it means subtraction of z. And sigma squared, well, I made a mistake here. It's just 2. Okay? Sigma squared is equal to 1. those specific numerical values for mu and sigma squared. Okay. So here's the fact. As a fact. If Z is the standard normal, random variable, then if you define X equal to sigma Z plus mu, then X is normally distributed with parameters mu and sigma squared. Just a quick idea to prove. The proof is this. Since X is equal to sigma Z plus mu with Z being the standard normal. Then, so this is normally distributed, and what we see is something like A times something normally distributed plus some number B. That random variable, X, is normally distributed. Normally distributed. With parameters so it was A times mu, the parameter here, plus B. Okay? So here, A is sigma, the mu for Z, okay, with this being standard normal, the mu for Z is 0, so it's sigma times 0 plus mu, which equals to mu, and, okay, I'm going to write here, what was it? It was A squared times sigma squared, where sigma was the second parameter for Z, that's 1. So here this would be A squared is here, it's A is sigma, so sigma squared times, well, the second parameter for Z, which is 1 squared, so that's just sigma squared. And I'm going to write this. This is by the previous fact. Previous fact. So that concludes that proof. The next thing I want to do is prove a fact about expected values that's in general. So here's a fact. It says, let X be a random variable. It's a continuous, discrete random variable. then the expected value of AX plus B is equal to A times the expected value of X plus B. And the way that we'll prove this is we'll prove this in terms of two cases, cases of discrete or continuous. So case one, if X is discrete, then the expected value of AX plus B, well, that's a sum over all X values of G of X, which is AX plus B, times F of X. And that's going to be equal to the sum, I'll rewrite this as X over X values of AX F of X plus, I'll split it up into two sums, X of B times F of X, which equals to A times the sum over all X values of X F of X plus B times the sum over all X values of F of X. A is A. The sum over all X values of X times F of X is nothing more than the expected value of X. That's its definition for a discrete random variable. This is B. And the sum over all X values that big X can take on of F of X, well, that by property of the PMF, that's what F of X is here, big X, that's equal to 1. So 1 times B is just B. I'll leave it at that. So that concludes the proof in this case. Case 2 is if X is a continuous random variable, then the expected value of X is equal to expected value of, A times X plus B is equal to the integral from minus infinity to infinity of AX plus B times F of X, which is PD of X, dx, which we'll say is the integral from minus infinity to infinity of AX F of X, A times X, F of X, plus B times F of X dx. So I'm going a little slower on this one, for which I will now insert one more step than I did in the previous case. I can break up into two integrals, AX F of X dx plus the integral of B F of X dx. Of course, we're running from minus infinity to infinity. A can be taken out. X times F of X, the integral of that, dx, so the whole line, plus the B can be taken out, integral from minus infinity to infinity, of F of X, dx. And just as before, this is the expected value of X, plus B times the integral of the PDF over the whole line. That's just 1. And so we get what we want in this case, so in all cases, we get the result. Okay. Next thing we want to do is we want to look at the expected value of a normally distributed random variable with parameters mu and sigma squared. as a fact, we're going to let x be normally distributed with parameters mu and sigma squared. Then the expected value of x equals to mu. And we'll prove this fact. So here's the proof. Okay. Well, first of all, note if z is the standard norm, random variable, then the expected value of z is equal to the interval from minus infinity to infinity of little z times its PDF, which I call f of little z, dz. Don't do it too fast, you get dz. So that was my joke. That's equal to the interval from minus infinity to infinity of z, let's pull out the constant, which is 1 over the square root of 2 pi, e to the minus z squared over 2 dz. We'll integrate this directly. So this is 1 over the square root of 2 pi. Remember, this is a really improper, it's really an improper integral, but I'm going to handle it informally without limits. This can be integrated where you think of the u being equal to minus z squared over 2, and thus du is equal to minus z. Well, I've almost got that, so it's really, when I put a minus z, put a minus in front here. I have to compensate by putting a minus here, and I'll rewrite this from minus infinity to infinity. So e to the minus z squared over 2 minus z dz, which we can rewrite as minus 1 over the square root of 2 pi. The integral of this is e to the minus z squared over 2, evaluated from minus infinity to infinity. When you let z go to infinity, this guy's going to go to 0. So we end up getting minus 1 over the square root of 2 pi times 0, and then this is going to be 0. And so that's just 0. Well, that's great. So we found the expected value of z is equal to 0, which is what we hope to have happen to make this statement true, because z is normally distributed with parameters 0 and 1, and so its expected value better be 0, and it is. Okay, so what does x look like? So x, it can be rewritten as sigma z plus mu. Okay, that's by our previous fact. So the expected value of x in general is equal to the expected value of sigma z plus mu. And by previous fact, just before that, this is sigma times the expected value of z plus mu. But we just found the expected value of z to be equal to 0, so that's sigma times 0 plus mu. which equals to mu. Hence, the statement. Only one more thing that I want to do. That's this fact. If x is normally distributed, with parameters mu and sigma squared, then the variance of x is equal to sigma squared. Let's prove that. Okay, so the proof, we normally use that formula. Variance is equal to expected value of x squared minus expected value of x to the squared, but not this time. So here, what we'll say is the variance of x, by definition, is equal to the expected value of x minus the expected value of x to be squared, which equals to the expected value of x minus mu to be squared, which we could rewrite as 1 over, so I'm thinking this is the expected value of a function of x. So it's 1 over the square root of 2 pi sigma integral from minus infinity to infinity of x minus mu to b squared times e to the minus x minus mu to b squared, all over 2 sigma squared dx. Here we're going to let y be equal to x minus mu over sigma. Then dx, dy, will be equal to 1 over sigma dx. Well, this is going to be equal to then. So I'll write down the expected value of x minus mu to be squared. It's going to be equal to 1 over square root of 2 pi times sigma. Here, this will be the integral from minus infinity to infinity. This right here is going to be, well, x minus mu is x minus mu divided by sigma is y. So this is really sigma squared y squared. That's what this is. Solve for x minus mu. Here, this is e. Okay, so x minus mu, I substitute in for that. I substitute y times sigma. It's minus y times sigma to b squared, all over 2 sigma squared. D, and here dx is the same thing as 1 over 1 over sigma. Okay? So that dx would be equal to sigma dy. So I'll write down sigma dy. That sigma and that sigma at the end cancel each other. So I'm left with 1 over square root of 2 pi. I can pull out a sigma squared. It's the integral from minus infinity to infinity. Here's y squared. E. This sigma is going to be squared. It'll cancel out with this sigma. So it's e to the minus y squared over 2 dy. Okay, so we've got to be able to work with this. And so the way that we're going to work with this is we're going to work with it through integration by parts. I'm going to rewrite it on this side of the board and just write down the integration by parts method here on the left side of the board. So what this is equal to, so here's where we were. Just rewriting that. 1 square root of 2 pi sigma squared. This is the integral from minus infinity to infinity of y squared e to the minus y squared over 2 dy. That's what we were. Previous line said that, so I just want to put it in. We're going to let u be equal to y, so we're doing integration by parts. Du will be equal to dy. We're going to let dv be equal to this, one of these y's. I've used one of them, keep the other one here. E to the minus y squared over 2 dy, and the integral of that, this is e to something, almost a derivative of something, you need a minus sign. So put a minus, and then compensate by putting a minus outside of the integral. And you get minus e to the minus y squared over 2 dy. So this is equal, I'm being very informal here, 1 over square root of 2 pi, sigma squared, it is times, it's u times v, so it's minus y, that's the minus, times y, e to the minus y squared over 2. This shouldn't have a dy. It needs to be evaluated from minus infinity to infinity. Look, this is very informal. Okay? You could have dummy variables involved there. You're taking the limits. And this is minus the integral of v du. So it's minus, and here's another minus, that makes a plus. Integral of e to the minus y squared over 2 from minus infinity to infinity. And then dy. This is equal to 1 over square root of 2 pi sigma squared. Here, you have to use L'Hopital rule in both situations, but if you do, you'll get 0, minus 0 plus 0. Plus, here, okay, what this is equal to, we've done this before in the very first thing we did today. This is equal to, I think, the square root of 2 pi. That's what this is. And so when you multiply this out, you just get sigma squared. And that's what results in the Okay, that's enough for this video lecture. I thank you very much for your time and patience.